In this lesson, we'll talk about inverse to the first-rate trigonometric functions, sine, cosine, and tangent. Let's recall the shape of sine function. It's a wave like this. If we treat this function as a relation and we would like to see the inverse of it, we need to look at the image of this shape in reflection in the diagonal. So this image is presented here. This curve will weave along the y-axis vertically. So such a relation won't be a function. And since we like to talk about inverse functions, not just relations, then the idea is to restrict the domain of the sine curve to one-to-one segment. For example, if we take the section from negative pi half till pi half, then this section of the graph is always increasing, therefore it's one-to-one, so it has an inverse, and the inverse will be a function. This inverse will be this part of the graph that we see on the right. So only this section of the graph will be our inverse of a sine with restricted domain negative pi half to pi half. This part is called restricted domain of the sine function. So only this section can be reversed. Obviously, we could take some other sections and reverse them. However, we like to take the section that is closest to the center. In summary, as we said, a function has an inverse, and the inverse will be denoted f to the negative 1, if and only if the function is one-to-one. Since sine is not one-to-one overall, we need to pick a section that is one-to-one, and the section that we usually pick is from negative pi half till pi half. And in this section, we can reverse the sign, and the inverse of the sine will be denoted sine to the minus 1 or arcsine. So this graph over here is a graph of arcsine. It is an inverse of this part of the graph of sine. And we can see these two functions in one system of coordinates. So this dotted line represents the function sine, and the solid purple is the arcsine. So as you see, the domain of arcsine is from negative 1 to 1, and the range is from negative pi half to pi half, which is exactly opposite situation that we had for sine. The restricted domain of sine was from negative pi half to pi half, and the range was from negative 1 to 1. Now we flip it. So that's the shape to remember: inverse sine or arcsine. On some calculators, this name could be written even as just a sine. That also means arcsine. But most commonly used notation is sine to the negative 1. That doesn't mean the reciprocal of sine. This negative 1 is a notation for inverse function. So don't confuse the inverse sine, sine to the minus 1, with the reciprocal of sine. That's not the same as 1 over sine x. And here we have a formal definition of arcsine. The inverse sine of x is such an angle, this is really an angle, such an angle y, that sine of this angle y gives you back the value x. So x is a value, the input for inverse sine is a value, but the output gives you an angle. The input oscillates between negative 1 and 1, like on this diagram, and the output is between negative pi half and pi half, from here to there, the same as on this diagram. Well, someone could ask, why do we have the name arcsine? It must have something to do with an arc. Well, let's see the situation in a unit circle. If we open an angle y, and this is a unit circle, then the length of the arc subtending this angle is also y. The height of the point defining this angle is x. So arcsine of x really represents the length of the arc in a unit circle, whose sine is x. Well, let's look at properties of our arcsine function. Here we have a graph, so we can look at it and read the properties. What's the domain of arcsine? Well, the domain is from -1 to 1. So, -1 to 1. Now, what's the range? The range is from -π½ till π½ So we can record this -π½ till π½ The function is increasing and the function is odd because it's symmetrical in the origin. Next, since arcsine of x is actually y, such that sine of y is equal to x, then the composition of sine and arcsine of x is always equal to x. Obviously, the input must be from the domain, so from -1 to 1. However, we have to be careful when we compose the other way around. First sine and then arcsine on the top of it. Because if we start with the input, which is an angle from the restricted domain of sine, that means between -π½ and π², then this composition doesn't change the y. The value of the composition is still y. We have identity. However, if our angle is not from the restricted domain but somewhere farther, for example, if I will extend my sine function somewhere here, and if I take an angle 3π², then the value of it is √2/2. The same value can be found in the first quadrant, which is π². That was our reference angle, right? So the composition arcsine with sine of the angle 3π² won't be 3π² anymore, because this value has to sit in the range of the arcsine. So it must be between -π½ and π². The value will be actually π². So inverse sine of the sine of 3π² will actually be π². What we've done is, because our angle 3π² was not in the restricted domain, we had to move this angle to the restricted domain, in this case to the first quadrant. So the value for arcsine of sine of y, if y is not in the restricted domain, is the angle that corresponds to y, but from the restricted domain. So y with the subindex domain in my notation represents the angle corresponding to y, but moved to the restricted domain. So the process of moving this angle to the restricted domain can be done just by looking at the diagram or by looking at the unit circle. 3π² is here, but we need to move this angle to either first or fourth quadrant, because that's the restricted domain. Let's highlight it. This is the restricted domain for sine. And since 3π² was in a quadrant that sine was positive, this needs to be moved to the quadrant that sine is also positive, therefore to the first one, so the 3π² corresponds to π². So as you see, if we compose arcsine and then sine, there's no problem, we can just nihilate them. The composition makes identity, so we end up with just x. But if we compose the other way around, sine with arcsine, we have to watch if the original angle was in the restricted domain or not. If it wasn't in the restricted domain, we have to move it to the proper quadrant. Okay, let's practice. Find arcsine of -1/2. Well, let's follow the definition of arcsine. This is such an angle theta. Remember, the value of any inverse function is an angle. So it's such an angle theta that sine of theta is equal to the input, which is -1/2 in this case. Okay, now since 1/2 comes from special triangle 1, 2, √3, so sine of which angle is 1/2? Oh, sine must be of that angle, which is π6. So we know that theta reference is π6. But now we also need to accommodate for the sine. The value of sine is negative. So we're really looking for a quadrant that will have negative sine value and that will also be in the restricted domain of sine. Therefore, either first or fourth. Only fourth quadrant has a negative sign. Therefore, our angle pi6 must be moved to the fourth quadrant, which is negative pi6. Therefore, final answer, our theta is equal negative pi6. The second example, inverse sine of 0.7. The composition in this way is just an identity, so we end up with the same 0.7. The next example calls for arcsine of sine of pi thirds. So the composition of inverse functions would disappear as long as this angle is in the restricted domain of sine. Is pi thirds between negative pi half and pi half? Yes. So this is equal to pi thirds. There's no problem here. And next example, again, the composition of inverse functions, we could nihilate them as long as the angle is in restricted domain. However, 4 pi thirds is not in the restricted domain from negative pi half to pi half. Therefore, we need to move it to the proper quadrant. Where exactly 4 pi thirds is positioned? Well, it's more than pi, so it's somewhere in the third quadrant. It's pi plus pi thirds, somewhere here. That's the angle. So it's a third quadrant, meaning the sign is negative there. Therefore, we need to move this angle to the fourth quadrant, to the restricted domain. That will be a negative angle. Since the reference angle for 4 pi thirds is just pi thirds, therefore this answer will be negative pi thirds, because the angle must be in the fourth quadrant. Let's see another example. Here we have arcsine of certain number, and this number is connected with half of a square with pi quarter angle, because it's 1 over root 2 or root 2 over 2. So this is certain angle theta, such that theta reference is pi quarter. Since this angle must be between negative pi half and pi half, and must result in a negative sign, so this angle must be in the fourth quadrant. So theta by itself must be equal negative pi quarter, because it must be in the fourth quadrant. Therefore, our expression turns out to be tangent of negative pi quarter. But tangent of a negative number is the same as negative tangent of pi quarter, because tangent is odd. However, we know that tangent of pi quarter is 1, so it's negative 1 overall. And finally, this expression. Here we have an angle theta such that sine of theta is equal 1/5. So what we can do, we can draw a triangle modeling the situation. Right angle triangle with angle theta here. Sine of it is 1 over 5, so 1 is here, 5 is there. And then we can answer the question, what's cosine of such angle? But then we need this side. So to find out this side, we use Pythagorean equation, so that will be 25 minus 1, which is root 24. But root 24, we can pull the 2 out, and it's 2 root 6. So cosine of such angle theta is equal to root 6 over 5. Let's look at cosine function. Here's the graph. The dotted line represents piece of cosine function. Normally it will go here and there farther, but we're picking only one section of cosine, the 1-to-1 section, in order to be able to take an inverse of it. So the idea is to take the section between 0 and pi, because the cosine is decreasing all the time, and it has an inverse. The inverse is drawn by a solid purple line here, only of this section of the graph. So that's our restricted domain from 0 to pi. Okay, therefore to find the inverse of cosine, we restrict the domain to the segment 0 pi, which means that if we look at the unit circle, the restricted domain of cosine is in the first and second quadrant. Sine, it was first and fourth, cosine is first and second. And similarly as before, the inverse function will be denoted by cosine to the minus 1 or arccosine. So the formal definition of arccosine is as follows. Arccosine is such an angle y that cosine of it gives you back the input x. And as before, the x oscillates from -1 to 1. That's the input for arccosine. And the y from 0 to pi. That's the output for arccosine. Looking at the graph, let's list the properties of the arccosine function. The domain of arccosine, as we said, is from -1 to 1. The range is from 0 to pi. The function is always decreasing. The composition of arccosine and cosine, because those are inverse functions, then they cancel each other and we end up with just x. However, the composition of cosine and arccosine, we have to watch if our input is in a restricted domain. If it is, we just cancel the arccosine with cosine, leaving us with the same angle. If it's not in a restricted domain, we have to move it to these two quadrants, either the first or the second. Okay, let's practice. Arccosine of -√2/2. Well, it's such an angle theta that cosine of this angle is equal -√2/2. So we can easily find out the reference angle because we know that √2/2 comes from half of the square. That's pi quarter 1 √2. This is the same as -1/√2. Therefore, the reference angle is pi quarter. But we need to move this angle to the quadrant that is first of all in a restricted domain of cosine, and secondly, the cosine by itself is negative in that quadrant. So theta is in the second quadrant, because second quadrant is negative. Therefore, theta is actually equal 3 pi quarter. If we move pi quarter to the second quadrant, that's pi quarter. Therefore, this angle is 3 pi quarter. So this is the final answer. In the second example, well, if we start with arccosine and then apply cosine, there's no problem here. These two functions annihilate each other and we end up with just -1. However, if we have the other way around, first with cosine, then with arccosine, we need to make sure that our angle is in a restricted domain. But yes, pi half, it is in the restricted domain from 0 to pi. Not a problem here. Therefore, as before, we can annihilate these two functions. We end up with just pi half. In the following example, we have the same situation, but we don't end up with 4 pi thirds because since 4 pi thirds is not in the restricted domain 0 to pi, it's higher than pi, then we need to move it to appropriate quadrant. Well, which quadrant? This angle was in third quadrant. 4 pi thirds is somewhere there. And cosine in third quadrant is negative. Therefore, we need to move it to the quadrant from the restricted domain of cosine. We need to move it to second quadrant. And if this is pi thirds, then the corresponding angle is 2 pi thirds because it's in second quadrant. So overall, this expression is equal to 2 pi thirds. Okay, let's see the next example. This is an angle, let's call it theta, such that cosine of theta is equal 1/2. Again, 1/2 comes from half of equilateral triangle, 1, 2, √3. So 1/2 is cosine of this angle, which is pi thirds. So this expression is really equal sine of pi thirds. And sine of pi thirds is √3/2. So we end up with just √3/2. And the last example, arc cosine of 1/5 is such an angle theta that cosine of theta is 1/5. Since this number doesn't come from special triangles, let's draw a modeling right angle triangle with angle theta here, and cosine is 1/5. So we can assume that this is 1 and this is 5, and we can calculate the third side, which is root of 25 minus 1 is 24. Again, this is 2 root 6. Okay, knowing that, we can complete the question. Tangent of this angle is 2 root 6 over 1, so it's just 2 root 6. And our last of the three functions to take the inverse of is tangent. Since tangent consists of many branches, like this, that's first branch of tangent around 0, then you will have a next one and the previous one, and they repeat itself. We need to take only one branch because, as you remember, our function must be one-to-one. So we are going to restrict the domain of tangent to negative pi half till pi half, which is this section of the domain. That's the restricted domain for tangent. And the inverse tangent will be denoted as tangent to -1 or arctangent. So here's the formal definition of arctangent. Arctangent of certain number x is such an angle y, this is angle, that tangent of this angle y gives you back the input x, where the value y, which represents our angle, oscillates between negative pi half and pi half. So if we look at this branch of tangent, after symmetry in diagonal, it becomes arctangent function, this thicker one. So that's arctangent function. And as you see, the values oscillate between negative pi half and pi half. And the inputs can be actually anything. So all real numbers is for the domain here. So let's look at properties of arctangent. The domain is all real numbers. The range is from negative pi half till pi half. The function is always increasing, and the function is odd because we have symmetry in the origin. We do have two asymptotes here. Those will be horizontal asymptotes. They become horizontal after the symmetry in the diagonal of the vertical asymptotes. So those asymptotes will have equations y equals negative pi half and y equals pi half. As before, if we compose arctangent with tangent, there is no problem. We can annihilate these two functions because those are inverses to each other. So this can be cancelled for any real x. However, if we compose tangent with arctangent, then we have to watch this input angle. In order to just simply reduce tangent with arctangent and be left with the same y, the angle must be between negative pi half and pi half. That means in the restricted domain. If it's not, we have to move this angle to the proper section of the domain. That means to the first or fourth quadrant. The same as for sine. So let's practice. Arctangent of 1. Well, we know that this is an angle, so it's such an angle theta that tangent of theta is equal to 1. But this is a very specific number. We most likely already know that tangent is equal to 1 for an angle that is equal to pi quarter. So theta is really pi quarter. If we don't remember this, it just comes from special triangle 1 over 1. The angle is pi quarter. That corresponds to this ratio. Now the composition arctangent with tangent, they annihilate, so we simply end up with just 100, not a problem here. But the composition of tangent with arctangent, we need to watch if our angle is in the restricted domain. So the question is it between negative pi half and pi half or not? Well, in this case, yes it is. So we don't have to worry, we can just reduce these two inverse functions. We end up with negative pi quarter. However, in the next question, this angle is not between negative pi half and pi half. Which quadrant is this angle in? Negative 5 pi quarters, so that's 4, 5 pi quarters, that's a second quadrant. Tangent in second quadrant is negative, and the restricted domain of tangent is the first or fourth quadrant, so these two. Therefore, the other quadrant that tangent is also negative would be this one, number 4. Okay, since this angle is pi quarter as a reference angle, then the overall answer here will be negative pi quarter. So this value is negative pi quarter. Well, let's see another example. Arctangent of root 3 is such an angle theta that tangent of theta is root 3. Oh, that comes from special triangle 1, 2, root 3. So tangent is root 3 over 1 for this angle. This angle corresponds to pi thirds. And pi thirds is in the first quadrant. Tangent is positive, everything is okay. Therefore, this is the same as sine of pi thirds. But how much is sine of pi thirds? Well, it's root 3 over 2. So we end up with root 3 over 2, final answer. And the last question, again, this is such an angle theta that tangent of theta is equal to thirds. Since this number is not from special triangles, we need to draw a modeling triangle with angle theta, and tangent is 2 over 3, so this will be 2, this will be 3. We can figure out what's the hypotenuse from Pythagorean equation. 3 squares 9 plus 2 squares 4, so that's root 13. And then we can complete the question. Cosine of this angle theta is equal 3 over root 13. And we can get rid of irrationality if we want to. So that will be 3 root 13 over 13 as a final answer.